All right. So we're going to continue our discussions on electric circuits. Okay. So last time we defined current, resistance, and then we introduced this law, very famous law, right? Ohm's law, which connects the current, voltage, and the resistance in a circuit. Okay. So now in this lecture, we're gonna first take a look at the power of a resistor. Okay. So this is still PowerPoint 9, slide 12. We learned this concept, power, in Physics 1, and I believe everyone is familiar with this concept, right? Power is defined to describe how fast energy is being transferred, right? So it's pretty much like velocity, right? We use velocity to describe how fast something is moving. And if something is using energy, we can define power to describe how fast it's using energy, right? So it's changing energy divided by changing time, okay? So this is the energy, it's not the electric field. Sorry, we do use a lot of the same symbol for different things in physics because we don't have so many symbols, okay? And then that's the general definition of power, right? Energy divided by time. And then this unit is joules per second, right? We have learned before, and we do have a new name for it, watt. So in an electric circuit, so this is a general definition for power, right? Anything is using energy or doing work, you can always define power this way. In an electric circuit, all these resistors, they are using energy, right? They're taking energy from the power from the battery usually, or from any power source. We can derive a special equation for resistors in a circuit. So this equation, this is a special equation only for resistors in a circuit, right? I times V, the current times the voltage, okay? So we can use this equation to calculate the power of any resistor in a circuit. So we're not going to derive that, we're just going to go ahead and use that equation. But this is still true in a circuit, right? This is still the general definition of power. Now let's take a look at the question on slide 13, okay? So if you buy a lot of things like a light bulb or hair dryer in the market, you always see a rated power on it and also rated voltage, right? So say if you buy a hair dryer, right, you just see the rated power on this hair dryer. It's 1300 watts, and the rated voltage is 110 volts. How do we find the resistance of this hair dryer? Okay, so let's see. This is how power is connected to current, voltage, right? But this equation doesn't have any resistance. But remember, resistance and current and voltage, they are connected, right? So that's pretty much the most used law in electric circuits, right? Whenever you don't know what to do, try Ohm's law, okay? So actually what I can do is this, right? I already know the rated voltage of this hair dryer. I only need the rated current. The current through this dryer when it's connected to this 110 volts, right? So I can divide both sides to find the, no, I'm sorry. We want the resistance. But if we want to find the resistance, we can just use Ohm's law by doing voltage divided by current. We know the voltage, if it's connected to 110 volts, the power of this thing is the hair dryer is gonna be 1300 watts. But we don't know the current. Well, that's how you calculate the current, right? You can rewrite this equation, find the current, and then plug it into Ohm's law. Okay, very straightforward. Okay, now you can pause the video and then find the resistance for me, all right? So this guy, you will get 11.8 amps, okay? And then you plug it into this Ohm's law, that's gonna be 9.3 ohms, right? Okay, this is very straightforward. Now let's take a look at the next question. An electric dryer, now it's a dryer, connected to a 110 volt source draws a 7.6 amps of current. We want to find the amount of heat generated in 3 minutes, okay? We use a dryer to dry clothes, right? So it does generate a lot of heat when it's running. Okay, we want to find the heat generated in 3 minutes. So in this case, the heat generated, just the energy it produces, right? So, and we don't know the power of this dryer, but if you know the power of dryer, power times time is gonna give us the heat, the energy it produces in 3 minutes. That's why the problem says find the energy in heat generated in 3 minutes, right? How do I find power? Again, this is a special equation for resistors for electric circuit. You use this equation, right? Find the power, and then use the general definition of the power to find the heat it generates in 3 minutes. Okay? So what are the numbers? The numbers I got, so that's very straightforward. You still do power equals I times V. That's 836 watts. And then you rearrange this equation. Remember, convert time to seconds, right? Everything must be in SI units if you do math in physics. So this guy, it's gonna be 3 times 60 seconds, right? So the energy, the heat it generates in 3 minutes, it's actually a very large number in joules, okay? 1.5 times 10 to the 5th joules, okay? That's power. Now let's take a look at the last question in this PowerPoint. So this is an interesting one. The voltage and power ratings of a particular light bulb, okay, which are in its normal operating values, 110 volts and 40 watts. Assume the resistance of the filament of the bulb is constant. So, okay, let's assume the resistance is constant independent of operating conditions. If the light bulb is operating at half the rated voltage, what would be the power of the bulb? Okay. So if I want to calculate power of a light bulb, I can still do this, right? So this is still a resistor. I can do I times V. So all I need to do is just find the, it's telling me that it's going to operate at half the rated voltage. So which is going to be 110 volts divided by 40 watts, right? So that's just going to be 55 volts. So all I need to do is just find the current of this light bulb when it's connected to 55 volt. In order to find this current, again, you're going to make use of Ohm's law. Whenever you don't know what to do, try Ohm's law. Okay. So you're going to do this, right? If you want to find the resistance of the, because the resistance of the light, but the problem says, let's assume the resistance is a constant. You can find the resistance. And if you can find the resistance, you do new voltage divided by new resistance, right? So you don't need to rearrange that. If you can find the resistance of this light bulb, you divide the 55 volts by the resistance, you get the new current, right? When it's connected to 55 volt source, and then that's going to be your power. And then how do you find the resistance? Then you're going to make use the rated values, right? Because the problem says when it's connected to 110 volts, the power is going to be 40 watts. So that's pretty much like the hair dryer problem we just did, right? The hair dryer has a rated power 1300 watts when it's connected to its rated voltage 110 volts, okay? So you can make use of these two guys and the old values to find the resistance, like what we just did with the hair dryer, and then use the Ohm's law to find a new current. So you're just using these two equations, right? And then find the current, multiply current by the new voltage, 55 volts, okay? So that's one way to do that. Another way, an easier way actually, you don't need to do so much algebra, is this. I just need to find the ratio of this new power to this old power, okay? Then I don't need to use the odd numbers and then do a lot of algebra, okay? How do I do that? So I want to find this new power, right? And the new power is going to be the new current times the new voltage, okay? And then the problem tells me that the new voltage is going to be 1/2 times the old voltage, right? So that's what I'm not going to use any number. I use symbols, okay? So then, if I can find the relation between the new power and the old power, then that's the ratio between them. I can use the number of this new power, the number for this old power, and the ratio between them to find this new power, right? So it's like this. If I can find the new power over the old power equals a number x, and then the old power is 40 watts, I multiply this old power by this x, I can get the new power, right? So that's my goal. So I don't need to do a lot of algebra. I just need to find the ratio between them, the connection between them. So how do I do that? So this is 1/2. So if I can find the relation between this new, I can write this new current in terms of the old current, then I would have old current here, old voltage here. When I multiply them, I should get the old power. And then if I still have some numbers there, the number is going to be the ratio between them, right? What is the connection between this new current and this old current? Okay, so you should be careful. You shouldn't assume it's the same, right? So people will say, oh, only the voltage becomes half, so the power is going to become half. So the power, new power is going to be half the old power, 20 watts. No, in this case, you should be careful because the new current is not going to be the same, right? The new current is going to be the new voltage divided by R. So this is just going to be the new current new voltage divided by the resistance, and then this new voltage is still going to be 1/2 old voltage right? Now you see that this is just 1/2 old current, right? Because the old voltage divided by R is going to give you the old current, okay? So that means you actually get 1/2 the old current times 1/2 the old voltage. Okay? So think about it, right? The new current, you connect this light bulb to a new voltage. The resistance doesn't change. The voltage becomes half. Take a look at this equation. Of course, this guy is going to become half, right? Because this number doesn't change, the voltage becomes half. So the new current is going to be equal to 1/2 old current. Now if you put them, factor out these two numbers, you get 1/4 the old current times the old voltage. This is the old power, right? Whatever these two numbers are, right? It doesn't matter. If I multiply these two numbers, I should get the old power. Right? So I already found the ratio between them, right? The old power, the new power actually equals 1/4 the old power. So the ratio between them is 1/4. Now you see that I don't need to do a lot of algebra. All I need to do is just plug in the old power, which is 40 watts. Okay, so the new power is actually 10 watts, not 20 watts. Okay, because both the voltage and the current become half of their original values, right? The current doesn't stay constant. All right. So this is this one. Now we're going to move on to the next PowerPoint 10. Now we're going to discuss resistors in combination, okay? We have done that with capacitors, so I hope this part is a little bit easier than the first time we saw them, okay? Again, there are two ways to connect resistors or any elements, right? Parallel and series, okay? So let's take a look at series first, because series is easier with resistors, okay? All right, I'm going to raise all of this. All right, so what is a series connection? That's every element connected one after the other, right? Forming a single path, okay, only a single path. Okay, So in this case, if I have like two resistors, and the resistors, a symbol for resistor is usually a zigzag line. Okay, so that's how we draw resistors in a circuit. Okay, you see that these two guys connected one after the other, so only one single path between them, connecting them. The path doesn't split, right? You don't see a path here or here, right? So no, okay. So again, we want to find, and you can see that because there's only one path, if one of these resistors fails, then there's no closed circuit anymore, right? So in this case, the whole circuit is going to fail. So everything is going to stop working, okay? So that's a series circuit. Now we still want to figure out this, the theory for a series circuit, what is the relation among the currents, the voltages, and also if I want to replace these two guys with one equivalent resistor, that's usually how we simplify a circuit, right? When we have a very complicated circuit, that's how we simplify the circuit. So now let's see. First of all, the current is easy to see, okay? So you see the current comes from the battery drives the current, right? Our convention is the current goes from positive to negative. So actually, if I call this guy has a current I1, this guy has a current I2, there's no difference between I1, I2, or I total, if we call this I total. There's only one path in this circuit. There's only one path for the charge to flow. So there's only one current, right? It's actually the same current everywhere, okay? So the current is going to be the same everywhere in the series circuit. So I hope this is intuitive, okay? Now what about the voltage? So the voltage, you see that this battery has a total voltage between these 2 points. So if this point A and B, right? So a voltage is just a potential difference, right? In a circuit, we usually call it voltage, but it's just a potential difference between 2 points. The battery is just going to provide a potential difference V total to the points A and B. Now you see that R1 and R2, they're connected one after the other, right? They're not, R1 is not directly connected to A and B. Only this end is connected to A. And then only this end of R2 is connected to B, right? So they will get the total voltage from the battery, but each of them doesn't get the full voltage. Each of them only gets part of it, right? And then if you add these two voltages together, you call them V1 and V2. So you add them together, you actually get the total. So each of them is just going to get part of the voltage from the circuit, okay? See, because this combination is connected to the A and B, so they will get the total voltage from the battery. But each of them is not directly connected to A and B, so they only get part of that. Now, the next thing we want to do is, so that's the relation among these voltages and the currents. Now, what about the equivalent? So if I want to replace them with an equivalent resistor, so what is the relation between this Req and R1 and R2? Now in this, if you look at this circuit, the Req is the only resistor connected to the battery, so of course it's going to get the voltage on it is going to be V total. It's going to get all the voltage. The current on it, through it, is going to be I total. Whatever this current is, it's going to go through everywhere. So this guy has a current. So okay, if you apply Ohm's law on this Req, you get Req must be equal to V total over I total. Now let's make use of these two relations. I can write V total as V1 plus V2. Now because I have two numbers at the top, I can split them up. I will get V1 over I total, V2, okay? Does this look familiar? We have done this, something like this in capacitors, right? Now I can make use of the relation among these three currents. This guy, let's replace this with I1 because they are equal. This guy, let's replace it with I2 because they are equal. Now this is just going to give me R1 plus R2. Okay, the theory is this, right? So if I have two guys in series, the REQ, which is equivalent to these two resistors, I just add them together, all the resistances together. If I have 3, add all the 3 together, right? 4, add them together. Okay, so that's very nice. So series circuit, very nice. Current the same, okay? Voltage is add, and resistance, you add them all. Okay. Now let's apply this theory in a real circuit. Okay, let's take a look at this circuit. So there is a battery. This is the question on slide 3. 12 volts. So I have a R1, 12 ohms, R2, 18 ohms, right? So we want to find the power of R1 and R2, okay? So this is obviously a series circuit, right? You see these two guys, they're connected one after the other. There's only one path connecting them. The path doesn't split. So this is a series, if I only look at these two guys. Now if I want to have power for each resistor, remember power has a definition, right? We have an equation for power for any resistor in a circuit, right? That's the equation we just learned, I times V. Of course, there's a general definition of energy divided by time, but we don't need to use this in this circuit, right? We can just use this very special equation for the circuit. So all I need to do is just find the I1, V1, and multiply them together. Find I2, V2, multiply them together. Right? So that's how, because this equation doesn't change. It doesn't matter how many resistors you have in a circuit, right? If I want to find the power of each resistor, I just multiply the current and voltage on this resistor, right? Then that's it. A complicated circuit is not going to change all these definitions, right? That's why they call it definitions. Now, okay, finding the current is easy, right? Remember, in a series circuit, there's only one current. Right? And how do you find the current? Well, very easy. So if you replace this with the equivalent circuit, okay, so this REQ is going to be equal to R1 plus R2, right? And then in this case, it's going to be 30 ohms, okay? So if you can find this current, I total, that's going to be the current in this original circuit everywhere, right? Remember, I1, I2, I total, well, there's no difference. There's only one current in this path, right? Because there's only one path. So if I can find this I total by using this equivalent diagram, right, which is just going to be V total over REQ, and that's going to be equal to I1 and I2 I need, okay? So that's how we find I1 and I2. Once you have I1 and I2, you should still find, you still find V1 and V2 so that you can find the power of each one, because you need the voltage, right? How do you find V1 and V2? The problem doesn't tell you. Remember, you can't use 12 volts for V1 and 12 volts for V2. That doesn't make any sense, right? Because they only get, each of them only gets part of this voltage. The sum of them is going to be 12 volts, right? So you know that V1 plus V2 equals 18 volts, or 12 volts, right? That's what you know. V1, V2, they're not going to be equal to 12 volts, okay? So how do I find V1, V2? You can always try Ohm's law, right, as I said. Now take a look at R1. If you know I1, R1, oh, V1 is just going to be I times R, right? So that's just going to be I1 times R1. And V2 is just going to be I2 times R2. But if you have found R2, I2, easy. Okay? You see that we're still using these two equations, Ohm's law and the power equation, in this circuit, right? We just need to know the how to simplify that, find the equivalent and I total. Okay? So, okay, so now you can pause the video and do the algebra, okay, see if you can find these two powers. Okay, so let's see. The I total, it's gonna be 12 volts over 30 ohms. So that's gonna be 0.4 amps, right? So that means I1 is gonna be equal to 0.4, I2 is gonna be equal to 0.4, right? So, okay, if I know I1 and I2, I can find V1 and V2, right? So V1 is going to be equal to I1 times R1. So this number times this, it's going to be 4.8 volts, right? And then V2, you can also find that it's going to be I2, R2, it's going to be 7.2 volts. And then to check if your answer is right, add these two numbers together, you will get 12, okay? You got the two voltages right. If you add them together, you don't get 12. Okay, you may have made a mistake, okay? All right, and then once you have done that, then the power of each guy is just gonna be I1, V1, and I2, V2, right? The theory doesn't change. The theory we have learned earlier doesn't change, right? The only difference is that now you have two resistors combined, okay? You just need to know the relation among all these currents, voltages, and resistances, okay? So this is going to give you 1.92 watts. And then the second one is 2.88 watts. All right, so that's a series circuit. Now let's take a look at a parallel circuit, okay? So a parallel, remember, what is a parallel connection? That's when you have these elements connected to the same 2 points in the circuit, okay? Don't have to be directly connected to battery. As long as you have some elements connected to the same 2 points, they are in parallel, okay? So if I want to draw a diagram, I would draw these two guys, right? So this is going to be the simplest diagram I can draw. If I have two resistors, right? So you see that both of them are connected to these 2 points. If I call it A and B. So they are in parallel. They're not in series, right? They're not in series, okay? So in this case, each resistor is totally independent of the other one, right? You see that this guy is totally independent of this guy. If this guy breaks, this guy opens. There's still paths for the second guy to form a closed circuit. So the second guy is not going to be affected at all, okay? So that's the advantage of a parallel circuit, okay? When they are totally independent of each other, okay? A failure in any one path is not going to interrupt the other paths, okay? Now what about the theory, okay? So the theory is this. We still want to find the relations among these voltages and currents and the resistances, because at the end, what is the equivalent of these two? If I still want to draw an equivalent resistor, which is totally equivalent to the effect of these two resistors together in a circuit, right? What is the relation between them? Now remember what we figured out for capacitors, right? If any two elements connected to the same 2 points, they will have the same voltage because they're gonna get the same potential difference between these 2 points, right? The voltage or the potential difference this guy gets is the potential difference between A and B. The voltage or the potential difference of this R2 is the potential difference between A and B. So of course they will have the same voltage. And in this case, if they are both connected directly to the battery, and the battery we call it V total, they will get the same voltage from the battery. As you can see that they are independent, right? They don't have anything to do with each other, right? So V1 and V2 actually they're the same. Now what about the current? Okay, so let's draw the current, right? So this guy, the battery drives the current. Let's call this I total. Then this I total is going to flow here. Now you see that now it has 2 paths to go, right? So this guy can go this path or this path. So that means I total actually is going to split up here. it's going to split into, if you call this I1, I2, right? So this is the current through R1. This is a current through R2. So the I total actually splits into I1, I2. So I total must be equal to I1 plus I2. And then you can check at this point, right? So I1 and I2, they're going to merge again and become I total, okay? So everything is consistent because the current is just going to be I total here, and then this is a combination. It doesn't matter, so the I total is going to come back to the battery, okay? So that's why the current, total current, is the sum of this current in each branch. Then what about, okay, we found this relation among these voltages and then currents. What about the resistance? Okay. Now again, if I replace this R1 and R2 with the equivalent, I want them to have the same effect in this circuit. The battery is not going to notice any difference. So to this REQ, it's just going to get the V total and I total because there's only one current, one voltage, one resistor here, right? So the REQ is definitely going to be V total over I total if I apply Ohm's law, right? Now let's make use of these two relations. So I can first write this I total as I1 plus I2. So I want to split them up so I can have like all values of R1 in one term, all values of R2 in one term. And then we can't split them up because they are the denominators, but we have seen this trick before, right? All you need to do is just take an inverse. Take an inverse of the REQ, you will get I1 and I2 go to the top and V total at the bottom. So now you can split up these two guys. I1 over V total plus I2 over V total. Now we're going to use the same trick because these three voltages together. I'm going to replace this V total with V1. I'm going to replace this V total with V2. All right, so the first term is just going to be inverse of R1, right? So it's going to be 1 over R1. The second term is going to be inverse of R2. Okay, so that's our theory. If I have the resistors in parallel, I have to do this inverse, okay? So 1 over REQ equals 1 over R1 plus 1 over R2, etc. All right? So if you remember the capacitors, okay, so they're pretty much like capacitors backwards. When capacitors in parallel, we add all these C's, right? When capacitors are in series, we do this inverse, okay? But we're not going to have capacitors and resistors on the same test, so you're not going to get confused, okay? But anyway, these are the theories you need to remember. But how do I remember the theory, right? All I need to do is this. I can remember one relation for either series or parallel, right? For example, if I remember, for parallel circuit, voltage is equal, so the currents must add, okay? The currents must add. And then the series and parallel, they're like backwards, okay? If I remember this is voltage is equal, currents add. So the series circuit is going to be currents equal, voltage is add, okay? That's how I remember that. Now again, let's practice this theory for parallel circuit. So let's take a look at the question on slide 6 and 7. So this is a circuit we get. There's a battery. And then now we have 3 circuits connected to the battery. Now they're back to battery. So these 3 guys, again, they are in parallel, right? Take a look at them. They are all connected to the same 2 lines, okay? So these 3 guys, they must be in parallel, okay? So it doesn't matter how you draw these lines, right? You don't need to draw them always with like 90 degrees, right? Because these are schematics, right? when you make a circuit, right, this circuit is going to be equivalent to that if I have 3 resistors with straight lines, right, the same, okay? Now I have this guy 2 ohms, the middle one 6 ohms, the bottom one 12 ohms, the battery is 2 volts. What are we finding in the first part? Find the total current through the battery. We learned that the total current is just going to be the current on each branch added together, right? So the total current is just going to be I1 plus I2 plus I3. If I can find these 3 numbers, right? So I would just call this guy I1, this guy I2, this guy I3, and then you see that I total split into these 3 guys, and then these 3 guys are going to merge, okay, and they become I total, consistent. Then how do I find I1, I2, and I3? That's when we use the relation among these voltages, right? Because if I want to find I1, I can use Ohm's law, which is just going to be V1 over R1, right? And what is V1? Well, because you see R1 is actually directly connected to the 2 volts. R2 is also directly connected to 2 volts. R3. So they will all get 2 volts from the battery, right? So this is just going to be equal to V total. And now you have these 2 numbers, plug them in, you find I1, right? Then you do the same thing for I2, and then you do the same thing for I3, you can find them. All right, at the end you add them together because the total current is the sum of all these currents if they're in parallel. All right, so now you can pause the video and then find these currents. All right, so this is going to be 2 over 2, 1 amp, right? This is going to be 2 over 6. This is going to be 2 over 12. You add them together, you get 1.5 amps. That's the total current through the battery. Now, what about the power of each resistor? Okay, so if you want to find power of a resistor, again, the power equation is still true. I times V, right? So I already have I1, I2, I3. So all I need is going to be V1, V2, V3. But wait a minute, V1, V2, V3, we just figured out. They're all going to be equal to V total because they are in parallel. So I have all the numbers I need, right? So I just need to multiply them together to get these 3 powers, okay? So now you can go ahead and finish this algebra. All right, so what do we get? So I'm just going to do I1 times V1. I already have these 2 numbers, right? 1 amp times 2 volts. So that's going to be 2 watts. Right, you do the same thing for the second one, right? It's going to be 6 times 2 volts, right? So this is going to give you 0.67 watts, and then the third one, what is the current? Times 2 volts. That's going to give you 0.33 watts. Okay, so all the theories we learned for a single resistor, they're still true here, okay? But you just need to know the relation among these voltages, currents, and resistances, okay, when you deal with resistors in parallel or series. All right, so I'm going to stop here for this video.